Hi everyone, welcome back to the channel. In today's video, we are discussion into these interesting circuits featuring an NPN transistor and a Zener diode and a pure resistor. Our main goal is to find out the current flowing through the 10 ohm resistor R3. Let's break down step by step. Alright, here our circuit. We have a 20 volt source here V1 and a 10 kilo ohm resistor R1 and the NPN resistor Q1 with the current again beta will be 99 and base to emitter voltage 0.7 volt and the 10 ohm resistor connected to the emitter terminal of the transistor and the Zener diode with the 6.2 volt is connected parallel to the resistor R2 and finally the our resistor R3 as a 10 ohm. Now first thing we need to consider is the role of this Zener diode. It is connected to the base terminal of the transistor Q1. This Zener diode maintain a constant voltage across it when it's in reverse breakdown. In this case, the voltage will be the 6.2 volt. So the big question is this Zener diode actually in breakdown in this circuit? To figure out that, we need to analyze the voltage and the currents. Let us assume for a moment the Zener diode is in breakdown. If that is the case, the voltage at the transistor, let's call it as VB and which is approximately equal to the Zener breakdown voltage 6.2 volt. So which is equal to Zener breakdown voltage VG. Now we know that for a forward biased silicon transistor, the voltage drop between the base and the emitter VBE will be equal to 0.7 volt. So if VB is equal to 6.2 volt, the voltage at the emitter terminal of the transistor VE is equal to VB minus V, which is equal to 6.2 volt minus 0.7 volt and which is equal to 5.5 volt. Okay, so if the emitter voltage is 5.5 volt, we can easily calculate the current flowing through the resistor R3. Let us call it as IR3. Using Ohm's law, the IR3 is equal to VE divided by R3, which is equal to 5.5 volt divided by 10 ohm. And by simplifying this, we will get 0.55 ampere. So based on the assumption that the Zener is in breakdown, we get the current of 0.55 amps through the resistor R3. But we need to verify our initial assumption about the Zener diode. To do that, let's look at the current around the base terminal of the transistor. The current flowing through the resistor R1. Let us call it as IR1. Voltage difference across it and its resistance. So that IR1 is equal to V1 source voltage minus base voltage VB divided by R1, which is equal to 20 volt minus 6.2 volt divided by 10 kilo ohm. So which is equal to 13.8 volt divided by 10 kilo ohm. And the current IR1 is equal to 1.38 milliamps. Now the current through the resistor R1 has to go somewhere. Some of it will flow into the base of the transistor, that is the base current IB, and rest other would flow through the resistor R2 and partially into the Zener diode, which we can call it as IZ. We know the relationship between the emitter IE and the base current IB is approximately equal to IE is equal to beta plus 1 times of IB. Since IE is equal to IR3, which is equal to 0.55 amps, we can find the IB. So IB is equal to IE divided by beta plus 1, okay, which is equal to 0.55 amps divided by 99 plus 1, which is equal to 0.55 amps divided by 100. And when we simplify this, we will get 5.5 milliamps. Now let's apply Kirchhoff current law at the base node. If the Zener diode were in breakdown and regulating at 6.2 volt, the voltage across the resistor R2 would also be 6.2 volt since it's connected parallel with the Zener diode. The current through the resistor R2, let's call it as IR2 dash, would be equal to VB divided by R2, which is equal to 6.2 volt divided by 10 ohm, and which is equal to 0.62 amps. Also we can call it as 620 milliamps. Now let's check the current at the base node with this assumption. IR1 is equal to IB plus IZ plus IR2 dash. When we plug this value into this formula, 1.38 milliamps is equal to 5.5 milliamps plus IZ plus 620 milliamps. That is equal to 1.38 milliamps is equal to 625.5 milliamps plus IZ. So that IZ is equal to 1.38 milliamps minus 625.5 milliamps, which is equal to minus 624.12 milliamps. We get a negative current for IZ, which is impossible for Zener diode in reverse breakdown. This tells us that our initial assumption that the Zener diode is regulating at 6.2 volt in this circuit configuration is likely incorrect. The voltage at base is not high enough to put the Zener family into breakdown, while also satisfying the transistor operating condition. So, what's really happening here? The transistor is likely operating in active region and the base voltage being determined by the voltage divider action involving the resistor R1 and the input impedance of the transistor base. The Zener diode in this case is probably not in breakdown and is acting more like an open circuit. If the Zener is not conducting, the base current flows through the resistor R2. Let's analyze the base emitter loop again without assuming VB is equal to 6.2 volt. We have V1 minus IR1 into R1 minus VB is equal to 0. So that the VB is equal to V1 minus IR1 into R1, and also VE is equal to VB minus VBE, and also IE is equal to VE divided by R3, and also IE is equal to beta plus 1 times IB, and again IB is equal to IR1, since Iz equal to 0. Let us substitute and solve for VB. So that current IB is equal to V1 minus VB divided by R1, and IE is equal to beta plus 1 into V1 minus VB divided by R1, so that VE is equal to IE into R3, which is equal to beta plus 1 into V1 minus VB into R3 divided by R1. And now we know that VE is equal to VB minus VBE, which is equal to beta plus 1 into V1 minus VB into R3 divided by R1. So VB minus 0.7 is equal to 99 plus 1 into 20 minus VB into 10 divided by 10k. So that VB minus 0.7 is equal to 100 into 20 minus VB into 0.01. So VB minus 0.7 is equal to 0.1 into 20 minus VB, and when we simplify this we will get 1.1 VB is equal to 2.7, so that VB is equal to 2.7 divided by 1.1, which is equal to 2.45 volt. So the actual voltage at base is closer to the 2.45 volt. Since this is less than the Zener diode voltage 6.2 volts, our assumption is that Zener is not in breakdown is correct. Now we can find the emitter voltage and the current through the resistor R3. This is more accurate base voltage. According to this, the voltage VE is equal to VB minus VBE, which is equal to 2.45 volt minus 0.7 volt, and which is equal to 1.75 volt, and the current to the resistor R3 IR3 is equal to VE divided by R3, which is equal to 1.75 volt divided by 10 ohm, and we can call it as 0.175 ampere, and there we have it. The current flowing through the resistor R3 will be approximately equal to 0.175 ampere. This example highlights the importance of carefully analyze the circuit condition to determine the operating mode of the component like Zener diode. Just because a Zener diode is present doesn't automatically means it regulating. What do you think? Did you find this analysis helpful? Let me know in comment below. Don't forget to like this video and subscribe for more electronics circuit breakdowns. Thank you for the watching. Thank you.